So this is the second in our webinar series towards deep transferable learning. Last week, we looked at the deep learning, what you might call the first half, and the second half, this week's focus is more on the transfer of learning. Let me take you back first to 2018. Have a look at this question, see if it rings bells. Feel free to make a comment in the chat. So you'll probably recognize this is a standard osmosis question, but they've switched the context away from potatoes to carrots. And at the time, this caused quite a Twitter storm. Students felt rather angry at AQA for having the temerity to do something that the students weren't expecting, and that they'd been taught something and they'd been assessed on something quite different. So what does that show? Well, I think this is the classic illustration of surface learning. In other words, you aim at the syllabus, you cover everything in the knowledge requirement, but it isn't enough to prepare students for that sort of question. So the way I look at it is, if you go through the first couple of stages of a learning sequence, you activate and then you spend this long time acquiring knowledge, you think that's enough, but actually they haven't learned to apply and analyze. Now, very often schemes, based around textbooks or worksheets and resources do tend to do that. And they give very much like lip service to the application analysis, just a few odd questions like this dotted around. And it doesn't seem to be enough, does it? Because students, if you look at it from the point of view of what's going on inside their minds, they might end up with quite a lot of knowledge, but it seems to be disconnected. And more importantly, it doesn't seem well linked to the kinds of problems that you want them to be able to solve. And as we'll see, there's a better way to achieve that match, which is what we call the deep transferable learning approach. In other words, we don't just aim at the syllabus statements of knowledge, we're focused more on the end point, which, as exams progressively move towards what students can do with their knowledge, means AO2, apply, and AO3, analyze. These are given just a sentence each in a specification. In other words, they don't tell you what every single knowledge statements would be applied and analyzed. They assume that you would be teaching the statements with that objective in mind, but it is easy to forget. And the benefit of doing that, of course, is that the students are more likely to connect the ideas, and if you've taught them how to apply and analyze, they should know which kinds of situations require which concepts and skills, and everything is better linked in their memory. So that's the objective. I think there's a further benefit, although research is still underway, it's difficult to prove. But over time, one would expect that if you focus just on the knowledge, you increase students' achievement. But basically, if they're, middle or low ability and their cognitive skills are not being enhanced, then they're not likely to make massive gains. Whereas the deep learning and transferable learning approach is trying to aim specifically at the cognitive processes that the better students already have, but the weaker ones struggle with. And if you train those, and we think you can, then they're more likely to actually become more able over time, which would, of course, increase their ability in a more exponential rather than linear way. So here's the agenda for today, 5 tweaks. We'll go through them quite fast, and I encourage you to ask questions along the way and think about the one that you most would like to try out yourself to see if it works. Number one, now this is the biggest mind shift of all, and this is the one I've been putting into the blogs and advertising to suggest to people that there is some surprising research here which kind of turns around the way normally people think about knowledge and solving problems. It's traditional to think, I do the knowledge, then they solve the problems. But maybe it's not so simple. Okay, so we have the goal in mind, right? This is a very difficult AO3 analysis question. And if you're aiming at deep transferable learning, you want students to be able to do this kind of question in GCSE. Have a quick look. Now, the examiners said that very few students got marks on this. Some of them managed to, interpret the graph, but they didn't link this with the photosynthesis and the biomass. So AO3 is actually very difficult, even if you have some knowledge. Now, what we think is that if you want the students to be better able to solve problems, you should use the best available research. And while it seems obvious that the tried and trusted way of teaching them things and then getting them to practice works, that's probably only true some of the time. If you want to get students to go to these higher levels, in fact, there is more to the best teaching approach than just having direct instruction. This is relatively recent research called productive failure. And I'm going to let the man himself explain to you for a minute what it means and why it works. But just in a very simple summary, what we're talking about here is before we deliver some theory to students, it might actually help for them to experience the problem, to struggle with it first, right? Screen. So I hope you enjoyed that if you haven't seen it so far. And basically what he's talking about is a different way of combining our goals. And we've done this in Blueprint, if you've seen those planners. There are two types of goals. Of course, there's the knowledge goal at the bottom, if we're teaching about temperature difference and what affects it. There is the big idea about the difference in temperature and the rate of cooling. But we've embedded that in problem-solving goals at 3 different levels. So in the acquire stage, there's the first problem of trying to help the teacher plan an investigation to test how the effect of a variable. And in the apply stage, we then are going to want them to use this in situations where variables affect the rate of temperature when they see graphs. And then they go to the analyze stage and have to draw conclusions from many sources of information. So this is the mix, right? Knowledge and problem-solving goals. And we want to involve students in the process of doing both. So roughly speaking, this is how it works in our course. And this is what our interpretation of Manu Kappa's research is. So at the earliest stage of acquire, before they learn the theory about why mass and temperature difference affect the heat loss, we set up a problem, which I explained last week. A forensic scientist wants to know time of death, which leads to a question about how quickly an object cools. And so that's the investigation, which the students are going to model. And then as part of that problem, and it doesn't matter if they don't get the right answer, and there's lots of guidance and structure, so it's definitely not discovery learning in any sense. Having thought about the actual phenomenon by doing the investigation or part of it, they are prepared to make more sense of the theory because they have all that background knowledge about the problem. That's the acquire stage. Then we move to the apply stage, and we have slightly more complicated problems with less scaffolding. new situations, the same knowledge. So here's about temperatures in beakers and graphs and calling. And you can see, I hope, how having done that acquire problem solving and the knowledge that goes with it, the students are more ready to be able to see why that knowledge also applies in this new situation. And then when we get to the analyze stage, we've added a new ingredient, which is more information here about food safety, the danger zone, where bacteria multiply. And so in this case, you're using the same knowledge, but the problems become more complicated and your response, like a 6-mark question, has to have more explanation and justification. I hope you can see then we've got these increasingly complicated problems as the basis for teaching the knowledge and preparing students for AO2 and AO3. So that's strategy number 1. Think in terms of problems, not just knowledge. But then the consequence is that we want to teach students how to solve those problems. And that's mostly the job of the apply and the analyze stage. And the reason that we want these stages to exist at all is because many students don't actually do it spontaneously. It would be great if you just taught them the knowledge and then gave them the practice exam questions and they could do them, right? But they generally can't. So we have to put this stage in. And there's going to be lots of scaffolding and there's going to be actual teaching of metacognition. As you know, these things work very well. And there's a long history of using teaching of cognitive processes in different subjects. So there are 2 basic strategies we can use. One is, for each concept, we come up with typical problems or problem types. So if it's cell transport, then this is one kind of problem, and there are several others that we could have chosen that are kind of the fodder for exam questions. So we're going to work through examples of each problem type in each concept. So in other words, we're going to prepare students with the most common kinds of apply exam question. And the second strategy is a general one that says, if we're going to solve a problem, we need a plan, right? How do we figure out what concept to use, what knowledge to recall, and how to get to the answer? So we try and teach them the 3 steps and what's involved so they can kind of generalize and automatize this approach. And now I'm going to show you how it works. In case you're wondering, this is definitely not any sort of fancy, progressive method here. This is definitely what you're used to doing, called gradual release of responsibility. I do, we do, you do kind of thing, but applied to problem solving. And the only difference, as you heard from Manu's video, is at the beginning, we thoroughly recommend students have some experience of the problem. They know what the problem is about and why they can't solve it. Because once they know what they don't know, there you have the motivation and the activation of finding out the knowledge, which is, of course, what you're going to give them. So this is demonstration, guiding, and then practicing. So how does it look? And this is coming from one of our practice books where we've created all these different problem types with worked examples and then your turn practice questions. So in the detect stage, the idea, of course, is to find the key information, find the unknown, and try and figure out what's the key concept that's going to solve it. Step 2, recall. Here, the issue is you might be able to dump all your knowledge onto the page, but you have to identify the relevant ideas that are needed in the problem. And then in the 3rd stage, what we want to do is to construct an answer. That should actually say solve, by the way, not recall. And one good way of doing that is to think about 3 parts to the answer. The claim is what you think is the answer, and then you give your reasoning and evidence to back it up. And we go through those kind of structures all the time in giving answers. Having demonstrated how to do it, the next stage is moving gradually to having students do it themselves. And there are various, if you like, steps that you can do this in. We think the first step is to give them pretty much the same problem, but change the numbers. And this is called isomorphic because it's exactly the same structure. So then they can do this. And the reason we do this is because the research suggests that part of the benefit of the worked example, as you've probably realized from teaching this way, is not when you're doing the explaining. It's when students are actually doing the solving, when they can go back and they can see how you did it. Because it seems to me rather ambitious to think they're going to follow everything you said and remember it, which is kind of just in case teaching. And often it works better just in time. Like when you get stuck doing something, you play that bit of the YouTube video to get you unstuck. And then having done the very similar problem, we get more and more different. We alter more features of the problem situation, which still use the same concept so that students can see, oh yes, I can see that it doesn't actually matter if I change this and this and this, it's still the same concept. So that's guide. And then finally, of course, there's the exam questions to practice independently. But as you can see, we wouldn't go straight from acquire to exam questions because you'd miss out this cognitive training in the middle. Tweak 3 is the kind of elaboration of this worked example cognitive strategy teaching, because it often doesn't work as well as we would hope. And we call this building self-explanation. Why? Because not everyone learns from worked examples. They may not be pitched at the level of every student who then can't follow what you're saying. And of course, it assumes an active role. The students don't somehow learn the worked example. They have to go step by step and go, okay, so first I do that. Why did he do that? Oh, yes, I can see why he did that. So this is self-explanation, and the best students do this, but many other students don't. So what we're going to have to do is to teach them how to self-explain, that it's important. And what we do in our problems in the practice book is, and here's an example of a physics problem, quite a difficult one using the laws of motion, is we put prompts into each stage. So this is the first stage where you're trying to figure out which equation to use. And we give the students some guidance and scaffolding, and we give them a prompt to see, do they know what that table means, right? Can they interpret that table? And then at the next stage, when we are trying to recall and solve, there are actually two ways, as very often there are in physics, to solve a problem that's a quantitative formula-based problem. And we introduce both of them, and we then ask students, which one do you think works best? So that's actually how to make sure that the worked example is effective. And we need one more tweak, in fact, to ensure that the whole approach is as effective as it can be. And that's because in shifting between showing it, giving practice, doing it yourself, we don't really know what level of scaffolding the students need to make those transitions, right? It has to be at the right level of challenge for each student. In other words, the cognitive load is variable. If you were tutoring a student, you would know very quickly how fast they could move from you showing them to them doing it on their own. But you've got a whole class and you don't. And it's important that that level of challenge is about right for different students. Or in other words, you have a problem that's kind of relatively challenging so that everybody can attack it. So it's got a high ceiling, but a low floor. And what we do is we try and set up the environment that there are multiple levels of scaffolding available, and you or the students can choose the one that's most appropriate. So you've got the worked example, which is maximum scaffolding at the top. And then you can move down to any one of these levels. You can set the problem, isomorphic problem that I showed you, where they just do the last step if you want to make it almost as scaffolded, or they can just do that problem on their own. Or to take away more scaffolding, you can give them the problem that's more different to the original with hints, or without hints to make it even more faded. And finally, of course, they can do the problems, and they can do them when there are other mixed up problems from teaching other concepts thrown in together, so they're not quite sure which concept to use. So there's a kind of hierarchy of scaffolding, and the idea would be to fade as quickly as you can to get to independence, but you've got all those multiple steps to choose from in between. So here we are with the last step, really, which is to go beyond apply, to go beyond analyze, and to do something that we call a transfer task. Why? Well, if we look at what we're trying to measure, we've got scientific ideas and knowledge. We've got inquiry skills or working scientifically. We've got these kind of cognitive processes or scientific thinking, and we've got metacognition, all these things we're trying to develop, but we can't do them all in the same assessment instrument. So if you've got quizzes and basic tests, you're very good at assessing the basic knowledge and some conceptual ideas. If you've got longer answers, you can assess the scientific thinking and some metacognitive ability, but they're not very real, right? If you want to integrate all those skills into a task, that's what we call a transfer task. So here's the difference. A traditional task on the right is basically a simplistic substitute or proxy, as it's called, of the real task turned into a sort of exam question. And it tends to reward surface learning if it's not a difficult task. And that tends to lead towards teaching towards the questions. So that's not too good. And what we really want to do is to make sure that the students ultimately achieve these goals, not only GCSE, but to be able to think scientifically, to be prepared for more complex science in university even. And so it makes sense to have one task that's actually authentic, that's actually like doing science. If it's an investigation or it's some sort of decision-making task, whatever, it's a worthy intellectual task, and it rewards deep transferable learning. And in fact, strangely enough, this can make assessment even quite motivating. Let me show you an example. Last time we did this webinar, someone had just used one of these microplastics activities that are free on our website and found that unlikely students who weren't normally very good at doing tests came up with some brilliant creative ideas to answer this, which she hadn't expected, and made them feel very proud of themselves. So that's another benefit, that students can shine where they don't normally do well in the tests. So this is microplastics. And the idea is that you'd use this at the end of teaching about particles, because it does revise knowledge of the size of particles and mixtures and separation techniques. So there's a context, setting up the problem. There's the fact that the actual problem source is the clothes in the machine when they're washed. Then there's a reactivation of the knowledge about the size of plastics and microplastics and particles. And then here it is, the question. So an engineer wants to design a filter to reduce the plastics coming out of the washing machine into the sea. How will they design it, right? So this is, if you like, the AO4 question. It's more difficult than apply and more difficult than analyze, because you've actually got to solve the problem and be creative in your solution, not just use the knowledge. That doesn't mean we can't scaffold it, because we put together a student sheet where you can go step by step, asking the students what's the knowledge here, and what would they do? How does it work? Can you illustrate it? So it doesn't have to be super hard, but it is authentic, and it does succeed in helping them put together all their knowledge and skill.